All right, so let's look at this example of how to use the power series to solve a differential equation, starting with just a linear first order equation with constant coefficients. Okay? First, we're going to assume this form for y. Okay? We're going to say that y is equal to this power series. And then we're going to compute the derivative. Okay? So if y is equal to this, then y prime is equal to that. Just take the derivative as we've done. Substitute y and y prime into the left-hand side of the differential equation. So the left-hand side is this. So you have this y prime plus y. Well, what's y prime? It's here. And you have y. Okay, that's just the assumed form. That's where that came from. Now, we want to combine those two terms, so we're going to have to shift indices and combine terms. So you always want to make this just equal to k, okay, for both of those. So for y prime, we're going to have k is equal to n minus 1. This gives us the solving for n. This means that we're going to substitute wherever we see an n at k plus 1. And we also care about where we start, so you just take n equals 1, plug it in here, you get k equals 0, and so this starts at 0. For y, well, we're just going to substitute, instead of n, just k. Just change the dummy variable, basically. That's all. Just so they have the same dummy variable. And they're starting at the same place. Okay, and they have the same power. So we could then, if you will, factor out that sum, and we end up with this, okay? So we've combined terms. In our left-hand side, in power series, looks like this, okay? Now, we're going to substitute the left-hand side of into the differential equation and set it equal to the right-hand side to obtain some recursion. Okay? So, our left-hand side we have, it's this. Our right-hand side is just 0. Okay? Here I write if the differential equation is non-homogeneous, substitute power series of right-hand side for the particular solution. Okay? So if we were dealing with a non-homogeneous equation, we would also, on the right-hand side, have to take the power series. Okay? Power series of 0 is just 0, so it doesn't show up here. And now how do we go from, so here's our differential equation in power series form. Okay, this is what our differential equation says. How do we go from here to saying that these coefficients are 0? This is the identity property, okay? Now, notice and pay close attention here. This being 0 just means the terms multiplying each xk is 0. It doesn't mean the c sub k's are 0. Okay? But the coefficients in the sense of what's multiplying xk, that's 0. Okay? We're not setting y equal to 0. That would give us that each of the cn's is 0. Here the differential equation is telling us that this is 0, which means the coefficients of xk, not the coefficients in here, are 0. Okay? So that's where that's coming from, by the identity property. And now solve for ck plus 1 in terms of ck. And this is what's called our recursion relation or recurrence relation, okay? And we get that k starts at 0. How do we know that? Well, that's where that sum started, okay? And the next step is to obtain these c's in terms of a base constant. So here you just say, okay, I'm going to assume I have c naught. Just take it as a constant. I then want to find out C1. So how do I get C1? I plug k equals 0 into this equation. And I get that whatever C naught is, C1 better be negative C naught. And then I go to k equals 1, or to get C2, and I say, all right, I'm going to plug in k equals 1. I get this with C1 there, using the current recurrence relation. And then I plug in what I have for C1, which is negative C9, and I get this. And I keep doing this, okay? And what do I get? I get a bunch of coefficients that depend on just C naught. So all I had to do was just specify C naught, and all of a sudden I have all the coefficients, okay? Now if I'm lucky, a pattern will develop, okay? And here we do see a pattern. We see this factorial pattern, okay? That's not always guaranteed that a pattern will show up, but here it does. And one might wonder, like, how many terms do I actually have to take and manually find? The answer is you have to take enough terms, okay? Enough until you get a pattern, or if you never get a pattern, then enough for the purposes you're working with. Like, say you're approximating some solution y and you just need the first 3 terms, well, then there's no point in going beyond that. So step 6, plug result of previous step into assumed form. So y is this by assumption, okay, which we could write in this expanded form. And now we could just plug in, well, what's C1? C1 was negative C naught, and that's where that is. Okay, C2 is 1/2 C naught, and that's where we're getting this. And so you have this expansion. And now factor out a C naught. Okay, and you get this term. And this could be written in power series. We do have a formula for the coefficients in closed form, which of course is not always guaranteed. But notice something. This looks awfully familiar. Okay, where is that coming from? Well, if you look at the exponential, it has this form. And if you plug in, instead of an x, you put minus x, you will get this. Okay? And so this is actually just e to the minus x there. And so our solution is y is equal to c naught e to the minus x, which we could have obtained, you know, going to this step and writing it as an elementary function is unnecessary. This is the solution that we're looking for. Okay, the interval of convergence is also, we know the interval of convergence of the exponential. But if we would have done this in terms of, like, say, a separable equation method, because we could have easily solved this, or linear equation method, we would have gotten this answer, okay? But here we get to see the power series solution. Finally, if we have an initial value problem or boundary value problem, we would just apply the initial condition or boundary conditions on this, okay? And something important here to pay attention to is that the constant, you know, when we were previously doing things, we would solve for a solution and we just multiply it by a constant, right? Say you have 2 linearly independent functions for a second order homogeneous equation, and you would just combine those c1 times y1 plus c2 times y2. Well, here this constant is just showing up as part of the power series. It's that first term. So that's something to pay attention to, is that this constant just kind of falls out naturally. And we get our solution y is equal to c times y1. Okay, this is a first order differential equation. So the fundamental set is just one equation. It's that one equation, e to the minus x.